Hello guys, so welcome back to our lectures. So we're gonna continue our discussion about amplifiers. So last time we discussed the transfer characteristics, and we learned that in the active region, basically here, when the relation between VO and V input is, or VCE and VBE, okay, is linear, we can use the transistor as an amplifier, and there will be a gain, okay. This gain is basically the amplification that you get. So, and of course, between cutoff and saturation, these two regions, you can use the transistor as, inverter driver, as we discussed. Okay. Now we're gonna, go deeply into the active region and the amplification, characteristics. So, this transfer characteristics here that we, give us a glimpse about how we can use the transistor in different ways is actually not so practical, because here we assumed that whenever the transistor or VBE is 0.7, the transistor will instantly become on, okay? And at some point, the input sat here, the transistor will be transferred to saturation region. Although it's not that, strict transitions. So basically the transition usually very smooth, okay? This has, a problem or some impact, that usually the practical range in which the active region is really linear, or the relation is really linear between VO and V input, is really small. So basically, the range in which we can use a transistor as an amplifier is really small. So let's get into that. So here we're gonna discuss today some very important observations about the practical transfer characteristics. The ones that we draw, that we plot, I just showed you this one. Usually it's good, you can understand some stuff, but this is a practical one, in which you don't have such, sudden transitions between regions. No, it's basically, there are some non-linearity, we can say. So here is, in this non-linear region, you have, it's an active region, but the relation between VO or VCE and V input or VBE is not linear. Also here. And only for a very small region, maybe from that point to that point, it's semi-linear. It can be approximated as linear, but it's not. It can be approximated or can be considered, or the non-linearity is negligible. We can say so. And basically, this very small range in the active region is the only region or only part that we can use the transistor, as an amplifier. Okay, but it was enough for us. And why is that? Because basically we want to amplify something. So basically, this signal that we want to amplify is small. So that's why even if this portion is small, still it can be enough for very small signals that we want to amplify. Okay. So here are all the observations that I want to discuss with you. We mentioned the first one, that not all the active region is valid because of the non-linearity, as we see here. Okay, and only the linear, semi-linear portion of the active region is valid for the amplification, application. If you want to use amplifier as an amplifier, if you want to use the BGT in a circuit as an amplifier, you must put the Q point, I mean VBE and IC, somehow or somewhere in that linear range. Okay, and your V input as well must adhere with that range. It can't be big. I mean, it can't be, if it was, bigger than this, for example, something like this, there will be a problem and we will see distortion. like what we see last time. Okay, either cutoff distortion or saturation distortion. Just review our last lecture to know that. Okay, why? Because basically here, VO and V input and VO or VC has non-linear relation. So there will be a distortion in the output. So the output may be something like this. It's not like the tip that we usually see with sine wave. Okay, or if it was bigger than this, I mean it crosses even the cutoff region, it maybe become like this. Which is of course worse. Okay, good. Also in amplifier circuits like this, okay, you have two types of signals superimposed on each other. Okay, you have the biasing voltages or the biasing sources, like for example VCC, or if you have for example in this case here, look, this is called V small BE capital. As we will learn in a moment, this means that this is AC and DC at the same time. So we can draw this circuit in that way. AC and DC. So this is DC, this is AC basically, and this is VCC, which is of course a DC. Now we have two signals. I mean, if you have an oscilloscope and you want to see the voltage at that point or the current flowing to the base, you will see it's DC voltage, and superimposed on that DC voltage there is an AC. Okay, actually it's clear here from the diagram that we can see. So if we clear it a little bit, if we remove that. So basically here, look at the input. So the input here is basically a DC, which is basically the distance between that point is a 0 and the center. This line in the center. And this DC is basically this value, V capital, BE capital. Then you have another AC signal, which he called here, the author, V small, BE small. So basically the V input, which he called here V small, BE capital, equal to V capital, BE capital. This is the symbol for the 0.7, for example. It's a DC. Plus a small portion or an AC portion, which is V small, B small, E small. Something like, for example, let's say 0.02 sine theta. So for example, the input might be like this, 0.7, which provides the biasing for the base emitter junction, and an EC portion, which is basically the signal that should be amplified. So this should be amplified. Or this is the input that we want to amplify at the output here. And look at the output. The output is more clear. Look, so the output here is also a DC, which is that level here, which is called V capital, CE capital, and also an EC superimposed on it, which is called V small, VCE small. So VO here is this voltage at that point. If you have a oscilloscope and you want to see, test the voltage at that point, you will see EC and DC at the same time. You will see something like this, a signal that is V capital, CE capital, plus V small, C small. This V small, C small signal, this is a symbol for the AC signal, okay, with the AC output, is basically the amplified version of this input here, or V small, B small, 0.02 sine theta. The amplified version means it was multiplied by some amplification gain. So V small c small should be something like this. Let's say AV, which is the symbol for the amplification, like 5, for example, 5, 6, 10, whatever, 100. That means it's amplified 100 times. Times 0.02 times sine theta. So the maximum here was 0.02. Now the maximum is EV 0.02. For example, if EV is 100, then this should be VC capital, V capital, C capital plus 2 sine theta. So the AC part has been amplified 100 times. Okay. So basically in amplification circuits, you have all the time, you have AC and DC at the same time. And for us to make our life easier, we're gonna analyze the circuit 2 times. One with the DC portion and one with the AC portion. We're gonna follow 2 principles. Yeah, 2 principles. The first one is that the superposition theorem. If you guys remember the superposition theorem, if you have 2 sources, you can get the current at any branch using one source, then another component of the current using the second source, then you add these 2 components together, then you get the final current. Okay, this is one principle. The other principle is basically some it's some assumption that we assume all the time that the signal input is small enough to be within that range in which the relation between the input and the output is linear. This is another assumption that we're gonna use that enable us to make 2 analysis, which is really easy. If you make the analysis with AC and DC component with each other, it will be hard because we must use at that time, the relations that IC is equal to IS exponential VBE over VT. And VBE here is AC and DC at the same time. And IC here is AC and DC at the same time. And we don't want to do that because, of course, we should, solve, iteratively and stuff like this, which is complex. Okay. Now, in the analysis, we need, to give symbols. Actually, I used such symbols. As I said, we have 2 types of signals. We have AC signals and we have DC signals. They are mixed with each other. So, and we're gonna do 2 analyses, as I said. We're gonna do DC analysis separately and AC analysis separately. Okay, and each one have its own, purpose. But we must do both. Okay, so we have 2 types also of the symbols that we're gonna do, or the currents and the voltage in the circuits. So whenever you give the symbol a capital letter and also the subscript, then this is DC. And usually the capital letters are used to represent the Q point parameters, or Q point currents and voltages. Q point is basically the operating point. For example, this is the operating point. How much DC you have. That's basically what's meant by the operating point, which is VCE capital and VBE capital here. Okay? And of course, IC capital, IB capital, and so on. So whenever you see the symbol itself is capital, the subscript is capital, both are capitals, then this is DC. How about small letters? Small letters is given to the AC components. So in the other type of analysis, when we analyze with only the AC part, as we will see, a lecture from now, in amplifier circuits, okay, we're gonna use all small letters, like look, I small, and even subscript is small. I small, B small, I small, E small, V for the voltages, V small, B small, V small, C small. Everything will be, small letters. So small letters represent pure AC signals. Capital letters, pure DC signals. How about, when you have both? If you wanna, we will not do that. But if we wanna do that, if we wanna do the analysis, with the AC and the DC at the same time. What we're gonna do? We're gonna mix. So we're gonna give something capital letters and give another thing small letters. So we're gonna give the symbol itself small letter, but the subscript will be capital. So for example, here is the symbol is small, a subscript is capital. So I small, C capital. This means the complete collector current, the current that flows in here to the collector, but with both components, AC and DC. So I small C capital is basically I small C small plus I capital C capital. I C small, I C capital, which is basically the AC part plus the DC part. That's it. Again, for example, for the voltages, V small, VE capital is a voltage between the base and the collector. This voltage here, this voltage has two components, AC component and DC component. So it is equal to V capital, B capital, the DC component plus V small, B small. To make it more convenient for you, take this example. That V small, this is small by the way, B capital is equal to 0.7 plus 0.02 sine theta. So this is basically small, B small, and this is basically V capital, B capital. And this is V small, B capital, subscript is capital. Okay, these are some observations that we're gonna use and we should know before we go forward and try go deeper into amplifier circuits. Okay, one more observation that we're gonna take in the next lecture, which is basically the next video, is basically the amplification and the transfer conductance. Okay, we gonna make a formal analysis to get the amplification gain, this guy here that I mentioned briefly, okay, for any amplifier circuit. Okay, thank you very much guys for watching this video and see you in the next video. Bye bye.